When we're talking about transformations of the graphs, we're looking at the A, the B, the D, and the C. Those all are going to tell us different things. If you're going to look at something like a phase shift, the B has to be factored out. So we have to have B and then parentheses around the x minus D part. If we have an equation like this, for sine or cosine, we can tell the amplitude. That's going to be the absolute value of A. That just means if the multiplier out here is negative, the amplitude is just the positive of that number. For the period, we're going to take the period of our original function and divide by b. If we have sine, cosine, secant, or cosecant, then our period for our new graph is going to be 2 pi over b. If it's pi, so this is for tangent or cotangent, then to get our new period, we just do pi over b. So you start with the period for the original graph and divide it by b to get the new period. For the phase shift, that is from the x minus d part. If we have a positive number in there, so for example, if we have x plus pi over 3, this is going to move it to the left. If we have a negative in there, this is going to move it to the right. Then for the vertical shift, that comes from the number that's added or subtracted on the outside of the function. So if we have a plus, that's going to move the graph up. If we have a minus, it's going to move the graph down. So these different things depend on different numbers that are in your function equation. So the amplitude comes from the A, the period has to do with the B, the phase shift has to do with the D, and the vertical shift has to do with the C. Now the next thing we talked about was some applications. There were lots of formulas, so there are some of these formulas that you will have on the test. One of them is the formula for arc length. It's S equals R theta. Now you'll have the formulas, but it won't tell you how to use them. A really important thing to remember about this one is that the theta has to be in radians. The formula for the area of a sector, same thing for this one, the theta has to be in radians. Angular speed is theta over t. Now this, we normally do the theta in radians. It just kind of depends on how the question is being asked. But for most of these other formulas, the theta has to be in radians, so usually we do that the same way. And then linear speed, the basic formula for this is v equals s over t. Sometimes though we used this with a combination of the formula for arc length. This is another way that we can look at the formula for linear speed. As far as what you'll be given on the test, it will be these 4 formulas right here. You won't have this because you can get this from taking this s and replacing it with r theta. So don't worry about memorizing these formulas. What you need to understand is how to use them and what the different symbols stand for. Now let's do some example problems. First, we're going to convert from the degree measure 465 degrees to radians. This is where you need to remember those unit fractions. So remember that pi radians equals 180 degrees. If we have 465 degrees, we want to use a fraction that has degrees on the bottom so that the degrees cancel out. That would be pi over 180. That way the degrees cancel, and we would take our 465 over 180, and this would reduce down to 31 over 12. So normally we would write the answer as 31 pi over 12, and that would be in radians. If we're converting from radians back to degrees, we're still going to use this fact, but now our unit fraction, we want to have degrees on the top so that we end up with degrees. And since this is technically radians, we want to have radians on the bottom so that the radians cancel. Also, the other thing that cancels here would be the pi's. So we don't have to worry about those. We just end up with -7 times 180 degrees divided by 10. And that simplifies to -126 degrees. Here's another one where we're converting from radians to degrees. This time we don't have a radian measure with pi in it, so this time we're just going to round this answer to the nearest tenth of a degree. We're still using the same unit fraction to convert this to degrees. Because this is still radians, we want the radians to cancel, so we're going to put that on the bottom. We're going to get an approximation for this just by putting it in the calculator. If we round to the nearest tenth of a degree, it's going to be 137.5 degrees. Now let's look at some more things that have to do with radian measure, and then using the unit circle. If we think about radian measure, remember that 1 full revolution is 2 pi radians. If we have a bicycle wheel that makes 3 full revolutions, then we can figure out how many radians it has rotated through. This is just going to be 3 times 2 pi. Our bicycle wheel would have rotated through 6 pi radians. The next thing is to find exact values for some of our trig functions. Now this is the same thing that we did in the last unit, it's just now that our angle measures are in radians instead of degrees. There are a couple different ways you can do this. If you want to take everything back to degrees and figure it out that way, that's one way to do it. One nice thing about the radian measures is that you have these families of angles that correspond to those special angles that we talked about. 7 pi over 6 is in the pi over 6 family. So for this one, we'd automatically know that our reference angle is pi over 6. That means if we figure out the tangent of pi over 6, then we can just think about what quadrant this is in and get the right sign, as in positive or negative, for it. So to do this, we can just figure out the sine of pi over 6 over the cosine of pi over 6. The sine of pi over 6 is 1/2. The cosine of pi over 6 is the square root of 3 over 2. If we divide these and simplify, we would end up with 1 over the square root of 3. If you wanted to put this as a rationalized denominator, it would be the square root of 3 over 3. Now that's for pi over 6. We still want to get the answer for 7 pi over 6. So we'd want to think about what quadrant this is in. If we draw a little picture of our unit circle with radian measures, this is 0, pi over 2, pi, and 3 pi over 2. Pi is the same as 6 pi over 6. So 7 pi over 6 would be just past that, which puts it in the 3rd quadrant. In the 3rd quadrant, tangent is positive. So that means our tangent of 7 pi over 6 is actually the same value we got here. Now let's look at the cosecant of pi over 4. Again, we can look at our reference angle just from looking what family this is in. This is its own reference angle. Then we just have to think about that this is the reciprocal of sine. The sine of pi over 4 is the square root of 2 over 2. So then we can just take this and flip it over and get 2 over the square root of 2. If we simplify that, we actually get just the square root of 2. This one we don't have to do anything extra because this was already a 1st quadrant angle. So we don't have to worry about changing the sign of this. Here's one where we've got the tangent of an angle and we're trying to find what the original angle was in radians. And this, you have to look at what quadrant this is. This would be the 1st quadrant since it's saying between 0 and pi over 2. So we just want to know what 1st quadrant angle would have this for a tangent. Now the problem is if you try to do this on your calculator with the inverse tangent, it won't give you the exact value, it'll give you the approximate value in radians. So what we can do is look at what tangent is. Since tangent is sine over cosine, we want to see what would give us the square root of 3 for an answer. And that would happen if our sine were the square root of 3 over 2 and our cosine was 1/2, because our denominators would cancel out and we would just get the square root of 3. So what we want to know is what angle has this for a sine and this for a cosine. That would be at pi over 3. So this is mostly just going back to your facts of the values at those special angles. We've got the same thing in this problem, only this, since it's between pi over 2 and pi, this is actually in the 2nd quadrant. So we can find our 1st quadrant angle and then find the reference angle to get our 2nd quadrant angle. To find our reference angle, we just want to look at where cosine is the positive square root of 2 over 2. So let's just call this x. In the 1st quadrant, that would be when x is pi over 4. Now we want to find the 2nd quadrant angle that's in the same family as this. So the 2nd quadrant angle that's in the pi over 4 family, and that would be 3 pi over 4. Again, if we look at our unit circle and put in these basic values, we want something in the 2nd quadrant that's a pi over 4. If you think about it, pi over 2 is the same as 2 pi over 4. This is the same as 4 pi over 4. We want something that's between those two, so that would give us 3 pi over 4. This time we're trying to find an approximate value instead of an exact value. We want an angle that's in the first quadrant. So we want to use one of our inverse trig functions on the calculator, but cosecant doesn't have an inverse function on the calculator. We're going to have to think about what the reciprocal function is, and that would be sine. We know that sine of s is the same as 1 over cosecant of s, since they're reciprocals. We can go ahead and put in our value that we have for cosecant, which is 3.6185. Now we know that sine of s is equal to this. Now we can use our inverse sine on both sides of that. Here the inverse sine and the sine cancel, so we just get s. So s is going to be the inverse sine of 1 over 3.6185. And that, if we do that on the calculator and round it to 2 decimal places, we get approximately 0.28. So this would be 0.28 radians.